Hello, good afternoon, everyone. Can you hear me, please? Hello, can you hear me? Good afternoon, everyone.
Yes, we can hear you.
Yes, thank you. It's my pleasure to join this Harmattan school to present this important topic, the physics of cancer treatment. Emmanuel Oyekunle is my name. I work at the University College Hospital Ibadan at the Department of Radiation Oncology. I believe it is a special privilege for undergraduates to learn about the role of medical physicists in healthcare. It is a vital opportunity that will prepare them ahead for those that will be interested in choosing this line of profession. So I congratulate the organizers of this program and many thanks to IPEM for the support. So my outline shows the following. In order for us to understand the physics of cancer treatment, we need to know what is physics, what is cancer itself, which is the problem that we are dealing with, the treatment modalities for cancer, relevant physics concepts, the applications to medicine, the radiobiology of cancer treatment, the equipment involved in cancer treatment, the role of physicists in radiation therapy, what are some of the courses that are relevant at undergraduate and postgraduate medical physics program, and conclusion. So what is physics? Our physical world comprises matter and energy. Everything in the world except energy is matter, is made up of matter. So we know that in science, in physics in particular, we are dealing with the interactions between matter and energy. So everything that you can see is matter. Matter is anything that could be touched physically. Anything you could see and you could touch is matter. So aside matter, the other constituent in the universe is energy. So there are different interactions occurring between these two important phenomena. So any problem also that deals with temperature, that has to do with size, motion, position, shape, and color involve physics. So physics sharpens our mind. It helps us to understand how to deal with different problems or how to explain how and why things occur. So physics plays a very significant role in our daily life. And we know that in physics, for those of us undergraduates, we have been dealing with measurements of different physical quantities. So in physics, we measure physical quantities. We cannot but measure quantities from one point to the other, or at one time or the other, we just must engage in measurement. So what is physics? So we could see that it is a study of matter and energy. Trying to understand the composition of matter. We know that matter is anything that has weight and occupies space. And we know that we have energy, different types of energy in our universe. So physics addresses the understanding of motion, what causes motion, its behaviors. Modern physics, we talk about nuclear physics, relativity, astrophysics, and the like. So physics in general tries to explain why things happen and how they happen. What is cancer? Yes, cancer is a disease. I believe many of us, we have had the word or term cancer at one point or the other. And people often ask that, what exactly is cancer? What does it mean? Or what causes cancer? What are those factors or things that cause cancer? It is actually a disease. And this very disease is as a result of abnormality of the body cells. We know that we have numerous cells in the human body, and these cells, they are expected to grow and divide in a defined pattern, in a normal pattern. So when the normal cells just stop, will not stop dividing or growing, then they become abnormal. So abnormal cells are cells that will just continue to divide without stopping. In other words, when certain cells in the body, when they have reached the point of stopping division and they just continue to divide or continue to grow, growing uncontrollably, then they grow to become tumors, they grow to become things that could be detrimental to the normal tissues, and they go out of hand and also spread to other parts of the body. So cancer is as a result of abnormal growth of body cells. Cells normally, they give signal to one another in order to inhibit growth when the limit of division or growth is reached. But cancer cells tend to inhibit the process of signaling, to one another regarding the need to stop growing. So growth will just continue and division will continue even when they are no longer necessary. And this is what causes cancer in any organ of the body. It could be cancer of the prostate, colon, head and neck. It is actually named after the region where it has originated from. So cancer cells that are associated with a prostate, for instance, will be called prostate cancer, and it can metastasize, that it can spread to other parts of the body as the disease becomes advanced. So this is what cancer is, as we need to understand what actually happens. So this is a picture. It is a picture of a tumor that is forming. So we will actually see that a tumor is forming. We can see the difference in the size and in the patterns of the cells at the middle of this structure. We could see that we have the abnormal cells forming. The cells are dividing in an abnormal way. They are also different in size and then pattern. So as they form, we will see that the cancer cells also go out of their boundary, go out of the limit set. So this is how they interact with normal body functions. They encroach into other normal tissues and they could spread to other parts of the body. For instance, somebody that has CA breast, cancer of the breast, can have some cells spread to the brain. You can also have metastasis to the spinal cord. So cancer cells spread easily, and that is why it becomes more difficult to manage or treat. So next, what are the treatment modalities for cancer? In order to understand the actual aspect that concerns us as physicists, we need to understand the other modalities that are available for treatment of this very challenging disease. And the first one is surgery. Surgery is a surgical procedure that is used for prevention and management of cancer. So in other words, surgery is not only to treat cancer, it can also be used to prevent or to support it. It could be curative in a situation whereby the disease is at a very early stage. It could be the primary mode of treatment. Surgeons will need to remove the mass of cancer cells, remove the tumor, and then the patient can receive maybe some radiation dose, or may not even require it. It could be preventive if it is necessary to do what? To remove polyps. For instance, in the cancers that involve the intestines. So if early detection is executed, the polyps, the precancerous tissues can be identified and removed before they form cancer itself. It could be for diagnostic purpose, whereby we can take tissues, samples of human tissue and analyze them in pathology department in order to know whether they are cancerous or to determine the likelihood of developing to cancer. It could be for palliative purpose, in order to relieve patient of symptoms, and it could be supportive in order to make it easier to administer chemotherapy, maybe passing catheter into the human body in order for drugs to be applied. So the second method is chemotherapy. You know, chemotherapy, the word chemical. So it involves the use of anti-cancer drugs to treat a host of cancerous cells. And there are many types of chemotherapy drugs that are available. How does chemotherapy work? Chemotherapy works by actually interfering with the cancer cells. Hello, can you hear me, please? Hello, are you with me? Can you see?
Yes, we can hear you. Yes.
So chemotherapy drugs, you know, they interfere with the ability of these cancer cells to grow. So this was the reason why I tried to explain what are cancer cells earlier on. So in order to interfere, in order to stop the growth of these cancer cells, then drugs have to be applied, and with the aid of these drugs, the ability for the cells to grow or reproduce will be inhibited. So these drugs will make the cancer cells, will slow down the growth process, and then make it difficult for them to increase in mass. And these cells, when they die, they can also be ejected from the body. So, but these chemotherapy drugs, they could be combined. You can actually have 2 or 3 combined together, and it could be applied in different ways, as we could see, even by injection intravenously, intramuscular, and the likes. But they often have side effects because these drugs work throughout the whole body. It affects other cells in the body. It is systemic. It is not confined to the area where the cancer cells are. So radiotherapy, which is also referred to as radiation therapy. Now, radiation therapy is an important component of treatment. Important component of treatment because about 50% of cancer patients will require radiotherapy at one point or the other, as a standalone treatment or to be used alongside other treatment modalities, maybe to be combined with surgery or chemotherapy. So radiotherapy involves the use of ionizing radiation to kill the cancer cells and shrink the tumor, reduce the size of the tumor. There are 2 main components of radiation therapy. External beam radiotherapy, which can also simply be called external irradiation, or another word for it is teletherapy. You know, we are familiar with the terms like television, telescope, and the like. So external beam radiotherapy means the source of radiation is coming from outside the body of the patient at a distance away, some distance away, maybe about 100 centimeters away, 80 centimeters away. So this radiation is coming, is generated from outside the body of the patient and is interacting with the body tissue. Brachytherapy, on the other hand, is internal radiotherapy, whereby the source is very close to the skin of the patient, is very close to the cancerous tissue. It is within the body of the patient. So there is often a link between the radiation and the body of the patient. So there's a connection using wires, using applicators that connect the machine, the equipment to the body of the patient. And this brachytherapy can be applicable to almost every part of the body once the applicators that are relevant to that organ or to that area of the body is available. So, but in external beam radiotherapy, there is no connection of wire or cables between the machine and the body of the patient. So, as I mentioned earlier, what happens is that radiation tries to destroy or damage the genetic material, that is the DNA, the deoxyribonucleic acid of the atom, and thereby discontinue the cancer's growth and division. So through this process, the cancer cells could be killed, but the effect of cancer cells will not be observed immediately. It will take some days or even weeks or months after irradiation. It's a gradual process. So normal cells will also be involved when radiation is used. Ionizing radiation is used to kill cancer cells, but they could recover. And that brings us to the important aspect of fractionation in radiotherapy. Fractionation means splitting the dose over a length of days, over a length of time. Splitting the dose, maybe a patient that is to be given 20 gray can be given in 10 fractions, 2 gray each, so that the normal cells, the normal tissues, they will have the opportunity to recover before the second, third, fourth fractions are delivered. So fractionation actually is important for the normal cells, but it is an important phenomenon, and it will depend on what how the doctor wants to kill the cancer cells, and then the part of the body that is involved. The goal of radiation therapy using ionizing radiation is in twofold. One, to damage as many cancer cells as possible, and also to minimize the harm that will be felt or will be received by the healthy tissues. So there are important physics concepts that we physicists we need to understand. Much has been said about radiation. So radiation is actually propagation of energy from a radiative source, the point where the source is generated, to another medium. So when energy is transferred from one point to the another, we could say there is radiation. And we know that radiation oftentimes we cannot see. We cannot see, when you are in a place where radiation is used, maybe you have gone for X-rays, chest X-ray, abdominal X-rays. Radiation is something that you cannot see, you cannot touch, you could hardly feel, the sense organs cannot detect radiation. And that is why it is important to measure radiation, as one of the speakers already said, to detect radiation, because you will not realize that you are being exposed to radiation unless it is measured. So it could be in form of electromagnetic radiation or in particulate form. And we could see the two classifications of radiation, the ionizing and the non-ionizing. So the ionizing radiation actually is in twofold. The charged particles, they are directly ionizing because they are able to cause the damage, to the DNA of the cancer cells through a single process. But the indirectly ionizing radiation, which comprises photons, they actually have to go through a two-step process. First, the release of charged particles through their interaction with matter, and then the charged particles cause energy to be deposited in the cells that are concerned in order to destroy the cells. So particular radiation comprises the electron, protons, and alpha particles. And the EM radiations are originating from the atoms, visible X-rays, gamma rays. So these are the common features of electromagnetic radiation. We know that they are propagated in straight line. The understanding of this is important. They travel at the speed of light, transfer energy from one medium to the other, and there's a decrease in energy, attenuation as energy traverses the absorbed medium. It is important to understand it so that while doing those calculations as physicists, you understand why the dose is reduced from one point to the other. The non-ionizing electromagnetic radiation, these cannot cause ionization. They cannot ionize atoms. They just don't have sufficient energy to cause ionization or to have a detriment on the human body. And we are familiar with radio waves, microwaves, and the like. So they do not pose any health risk to the human body. Ionizing electromagnetic radiation. Yes, the X-rays. As we learned yesterday, it was discovered by German physicists. So this indicates the important role of physicists in radiation medicine, because the major tool, X-rays, was identified or discovered by a physicist in 1895. X-rays are produced extranuclearly outside the nucleus. They are generated not by radioactive decay, unlike in gamma rays. And we could see that the energy would depend on the atomic number of the anode, and also the velocity of the electrons. So what determines the energy that is produced, energy of photons, X-ray, will be the magnitude of the electric potential, the energy that is introduced to accelerate the electrons in order to hit the IZ targets, in order to produce X-rays or photons through Bremsstrahlung. Gamma rays. Gamma rays, on the other hand, are produced due to instability of the nucleus intranuclearly, that is, within the nucleus. It is highly penetrative, as we know that gamma rays can penetrate deeper than have some particles, like alpha particle, which is heavy, much heavier than gamma rays. The decay of gamma rays, could be defined. I mean, the energies. In radiation oncology, radiotherapy, a very important radioisotope in use is the cobalt-60, which has 2 gamma rays. So 1.17 and 1.33. So the average of this is 1.25. So it is monoenergetic. So that is why the use of cobalt-60 is actually limited. The application is actually limited because of the limited energy that is involved. So as mentioned earlier, ionization is a process of causing ionization, in cancer cells, in the human body, the removal of electrons from atoms and molecules. And this is only attainable when the radiation has energy that is high enough to remove electrons, energy that is high enough to overcome the binding energy of the electrons to the atom. So 12 eV is considered the lowest energy attainable by ionizing radiation. Otherwise, the ionization will not be possible. There are some important radiation quantities in radiation therapy. It is important to be able to quantify radiation in order to be able to use them appropriately, and also in order to reduce to avoid errors, performance of error in dosimetry or in those calculations, because radiation that is delivered to the body of the patient cannot be removed again. So it is important to quantify using the right unit. Exposure is actually the amount of ion pairs that are produced in air by photons. So it is limited to measurement purely in air. Absorbed dose, on the other hand, is the amount of energy that will be deposited or absorbed in a unit mass of absorbent material. And this is actually the main unit of radiation dose for prescription and measurement in radiotherapy. So when a patient is to receive a certain dose for treatment of cancer, it will be specified in gray or centigrade. For instance, 1 gray will mean 100 centigrade, 2 gray will mean 200 centigrade. And this is actually the units that will be used for treatment planning and for those calculations. So it is important to understand these basic units. The other unit is rad, and actually 100 rad will be equal to 1 gray, or 100 rad will be equal to 100 centigrade. Equivalent dose is actually an important dose, that is important for radiation protection assessment. Is actually a way of quantifying the damage that could be expected from radiation. The damage that could be expected from different types of radiation, knowing fully well that we have particular radiation, we have photons. So the effect of these different types of radiation vary. So equivalent dose is taken into consideration the absorbed dose to a particular organ and accounted for the effectiveness of radiation. For instance, photons are known to have quality of 1. Photons, X-ray gamma rays have quality of 1. But when you compare it with those, maybe those from proton, from alpha particle, then you can have higher magnitude of damage. So it is measured in sieverts, and also equivalent dose can also be referred to the unit for assessment of personnel, that are exposed to radiation. So this is given in sieverts and not in gray. I'm sorry, I omitted information regarding effective dose here. Effective dose is actually when we are quantifying dose to the entire body of human, the entire body, not limited to one. So the cumulative dose to the entire body is actually the effective dose that also could be evaluated. Radioactivity, which is simply called activity, is also an important phenomenon that physicists need to understand and realize their importance in radiation physics or radiotherapy physics. So activity is the number of disintegration that takes place per unit time And it is because of the instability of the nucleus. When you have stable nucleus, the number of protons and neutrons that are not equal. The unit, we have the old unit becquerel. The new unit is becquerel, while the old unit is curie. And we could see the relationship between curie and becquerel. We know that radioactivity, follows a spontaneous process, and radioactivity explains why we have decay in radioisotopes in order to achieve stability. And so that is a unit of measurement. We also have the radioactive decay law. So decay law explains how to determine number of atoms during the decay process. And it is important in radiotherapy because it helps us to also be able to evaluate theoretically what is the quantity of charges that we require after a period of time, or what is the dose rate that is required after a certain period of time has elapsed. So this is a fundamental equation that is applicable to dose rate, to charges acquired, and also to many things in radiotherapy, as we will see later. So we could see that N is the number of atoms that will be attained or that will remain after a period of time. N naught is the original number of atoms, and we have the decay constant. So this is the formula. We also have the TH, which is the half-life of the isotope that is involved. So half-life is another important concept which must be understood. And looking at half-life, we need to understand the fact that radioisotope, they differ in half-life, and half-life is specific to a given radioisotope. So cobalt 60, we always have half-life of 5.26 years. Iridium, we have strontium, technetium. So a good example, a question to ask would be, what would be the decay rate of cobalt 60 in a space of 1 month? If cobalt 60 that is used in radiotherapy, what would be the decay rate? So this could be calculated knowing fully well that within a space of 5.26 years, the activity will decay by 50%. Within a space of this half-life, there will be a reduction by half. So if over a period of 5.26 years, we have a decay by 50% decay, then you can work it down to what happens in a month. So in a month, it will be approximately 1% decay in a month. So this helps us to actually understand the importance of the decay law. And it is important to know the half-life for each of these of radioisotopes that are used in radiation medicine. The importance of knowing half-life will determine for how long each radioisotope will be used. It will also help us to determine what to expect from them and the risk that is associated with this radioisotope. It also helps us to understand the irradiation time, the length of time for which a patient can be treated using this radioisotope. For how long a patient could be under the influence of the beam, the radiation that is emanating from this radioisotope. So it's a very important concept that physicists need to understand very well. The inverse square law. Yes, inverse square law is also another important concept for physicists, which is important in radiotherapy. It is actually the reduction in the intensity of radiation with the square of distance. Square of distance away from the source. And that is a formula. Intensity is inversely proportional to the square of distance from the source. So as we could see from this point here, this is a source of radiation. So as the distance from the source of radiation doubles, we'll see that the area quadruples. The area becomes ×4, it quadruples, and when that is done, we have a larger area. So the radiation amount will now have to cover the larger area, and by so doing, the intensity of radiation will reduce proportionately. So we could see that the intensity of radiation will reduce as distance is increased. So here it will be 9-fold, here it will be 4-fold. So, and this inverse square law is of high relevance in radiation protection, also in radiation therapy. A good example of it is when we set up patients for treatment using a teletherapy machine. We discovered that definitely the beam, the brightness of the beam, the intensity of the beam will reduce as the table moves further away from the source. So inverse square is of high relevance, and it is an important phenomenon that should be understood. So these are the applications of this concept in medicine: imaging, ionization, radioactivity. In radiotherapy, ionization, the concept radioactivity, the decay law, half-life, inverse square law. In nuclear medicine, we have decay law, half-life, and in radiation protection. So these concepts are very important. It's important for physicists to understand this. That is why having a first degree in physics is a prerequisite to being a medical physicist, or being in medical physics profession, because these concepts are things that theories that we need to make use of from time to time. Radiobiology of cancer treatment, it is important to know that the effect of ionizing radiation will depend on a number of factors. So how will radiation be useful in killing cancer cells or in treating cancer? It is because the energy of radiation is sufficient enough to cause ionization. And that is why in radiation therapy, the energy is in order of a megavoltage, a million volts, because of the need to be able to sufficiently destroy the cancer cells. So it will depend on the energy of radiation, the intensity, the structure of the tissue that is being irradiated, also the age and the general health of the patient. So these are important factors that will determine the sources of cancer treatment using radiation. And importantly, linear energy transfer is a phenomenon, or a parameter that helps to explain how energy is transferred to the tissue. It is actually the quantity of radiation that is delivered in the medium, such as tissue, per unit length, per unit track length of the radiation. So per unit track length of the material through which it traverses. So it is a function of the charges, the velocity of the radiation, and it will also determine the effect, the severity of the effects in the human body. So the high LET radiation, actually the particulate radiation, and the higher the LET, definitely the higher will be the probability of causing DNA damage. So this is a cobalt 60, we could say. It is very small radioisotope in teletherapy. The treatment that we use in cancer treatment, we can categorize them. We have the isotope-based machine, those ones that deals with, that make use of isotope, radioisotope. A very important one is the telecobalt machines that use cobalt 60. We could say this is the diameter of the isotope, range from 1.5 to 2.5 centimeter. And it is important to choose the right diameter so that you don't have much to reduce the effect of penumbra, which is often at the edge of the beam, reduce dose rate at the edge of the beam to reduce the effect. So choosing the right diameter of the cobalt 60 is important, and also the diameter will also determine the cost of the radioisotope. So in telecobalt machine, the source is always decaying; it constantly decays. So we can say that the energy that is produced is monoenergetic, unlike in the use of linear accelerator, which we soon see, that involves a spectrum, electromagnetic spectrum, energy spectrum, where we have arrays of energy. So here we have defined energy. So the source is able to remotely move from a shielded point to unshielded position in order to deliver radiation dose. And it is often done at a specified source to stage distance. So 80 centimeter for the cobalt machine. So this is a good example of a modern cobalt 60 machine. So here we have the Isocenter. So the Isocenter is an important point. It is a point where you have the rotation of the couch, the gantry, and the patient, meet at the same point. So it is important that treatment is done, calibration of the beam is done at the machine Isocenter. Which is often defined as 80 centimeters from the couch can move longitudinally east, and it can also move vertically up and down, somewhere around here when it is at rest, when the machine is not in use for treatment. So when it is time for treatment, when treatment is initiated, the source automatically drives, there's a drawer that, so there's an opening within it that opens up for the source to move to this point, and it stays here and then deliver the needed radiation dose. So this uses a cobalt 60 radioisotope. So another type of isotope-based machine is high dose rate brachytherapy machine. Brachy is a Greek word for short. So in brachytherapy, the source is closer to the tumor, and it involves radionuclides. So high dose rate brachytherapy involves radionuclides that have high activity per unit per unit mass, specific activity. So, and the source are very small. They are much smaller than the source that we have in order of millimeters. The diameter, maybe 6-7 millimeter, very small miniaturized radioisotope. So this is what we make use of in brachytherapy. Because of the nature of treatment that involves wires and applicator, the source must be very small. So in theory, the dose rate should be greater than 12 gray per hour by definition. But in principle or in practice, we have dose rate that as high as 350 centigrade per minute that offers this at 1 meter from the source. In high dose rate brachytherapy, you could treat for 10 to 20 minutes or 25 minutes. In order of minutes, treatment could be delivered because of the high activity sources that are used, such as iridium and cobalt 60. Because of the difference in the air camera strength, I will not want to go into that. The time to deliver treatment will differ between iridium and cobalt 60. So the nominal activity for iridium 192 at the beginning, when it is supplied, will be minimum of 10 curie, but for cobalt 60, 2 curie. So 2 curie will be equivalent to 10 curie, by source strength, because of the differences in their radioactive properties. So we have brachytherapy equipment. We could see this is a smaller equipment. They are movable, and we could see this is a wire. We can have a wire. This is like a guide wire that connects the machine to the patient. In this case, this is sterilization chamber, which is used for dose measurement. Yes, this is also a picture of the applicator in situ, applicator inside the body of a patient, in this case, cervix cancer. So we have the uterus, the intrauterine tube in the uterine cavity. We have the ovoid, the ring. So we have this in place. So this applicator carries the radioactive source. So the source drives into this applicator and delivers the treatment. So the treatment is much closer to the tumor that is being treated. So we have, this is a cylinder applicator. We have the ring applicator, which I also use. This is a case of prostate treatment done using needles. The needle is in place. So we could see that the needle is in place and it is being guided by the use of ultrasound. So we have the organ arteries, the normal structures around the uterus, which must be spared as much as possible. I mean, they must be preserved. Doses should be minimized to them as much as possible. So the low dose rate technique just simply involves the use of low activity sources like cesium-137. The dose rate is much smaller. Treatment could be for hours, 8 hours. It could be for up to 2 days, for hours to days. Instead of treating patients for a few minutes as it is, for high dose brachytherapy, it could be for some hours or days. And it follows the same principle with the high dose rate technique, except for the time duration, high discomfort to the patient. You also find out the fact that the risk of radiation exposure because of the high I mean, a long treatment time that is involved. Yes, the non-isotope-based equipment, linear accelerator. This is a very important equipment for external irradiation of cancer cells. X-rays are produced through the process of Bremsstrahlung acceleration of electrons, to which IZ target. We have in megavolts, and then the electrons. The electrons are also produced. So the electrons are monoenergetic, noting the difference between NV and MeV. So, but for the X-rays, we have the energy will depend on the electric potential that is used, to drive, to accelerate the electrons to the target. So the electrons are accelerated in principle via the waveguide of the LINAC, and the collision occur and high energy X-rays are produced. So patients are set up using the source axis distance approach, unlike in telecobalt machine where the method uses the source to skin distance. So we have in this place the Isocenter of the equipment, so which is important for machine calibration for dosimetry. So we have the couch, it could rotate around the patient. So, and you have, as this very point, as I was mentioning about the issue of inverse square the other time, as this couch, is lower down, the feed light of the feed size set will become bigger. The area will become bigger, and then the intensity of the radiation or the feed also will reduce. So this is a linear accelerator that do not make use of a radioisotope. Yes, very important equipment. I'm almost reaching the end. I'm sorry, it's so much to cover. Is the use of ionization chamber, which is an indispensable tool for those measurements for physicists, detectors, and they are very important for measurements. Very important for measurements. We have the cylindrical ionization chamber, the parallel plate, so which can be used for those dosimetry. Thermometers, barometers, these are also important. So we could see here the temperature pressure device, measuring device. We could see different ionization chambers that could be used for dosimetry task. It is also important as physicists to understand that we make use of phantoms. Phantoms are models. That are made of tissue equivalent, and they are often used to mimic or to simulate what will happen when the human body is not in place. So because we cannot experiment with the human body. So phantoms could be for a specific organ or for the entire body. So physicists in radiation oncology carry out their experimental work using phantoms in order to study distribution of doses within a given area, and also to see what will happen to normal tissues, and also to be able to quantify the output of the machine. What the machine is able to deliver per unit time, in order to be able to successfully carry out those calculations and achieve the goals of radiotherapy. So these phantoms could be used with detectors such as ionization chamber or thermoluminescent dosimeters, which was earlier explained by a previous speaker. So we have examples of phantoms. So we have these phantoms, lab phantoms. So of different different depths could be used in order to be able to achieve the purpose of dosimetry. We have the anthropomorphic, the air phantom, and we have this is popularly used in radiotherapy. The water phantom. The human body is made up of a large volume of water, and over 80% of water. So water is seen as a good phantom, a suitable one, and is very cheap, to find. So we have the IMRT verification. So these phantoms are used for dose measurements in order to quantify dose, to determine the dose from the machine, in order to be able to deliver the right dose as required by the clinicians. So conversion of measured charges to, so as physicists, what we are expected to do is to be able to convert the measured charges that are obtained through the use of ionization chamber when the radiation interacts with the air in the sensitive volume of the chamber, and be able to produce charges which are collected. So these charges are then converted to dose using this equation. The charges will be corrected for temperature and pressure. It is important to correct for temperature and pressure because we know that the mass of air in the sensitive volume of the ionization chamber is influenced by temperature and pressure. So it is important, and ionization is indirectly proportional to the mass of air in the chamber. So it is important to use this correction factor to be able to correct to the atmospheric temperature and pressure, and also knowing fully well that the chamber and the electrometer must be previously calibrated, so the dose to water can be calculated, and then this can be seen as the output, can be taken as the output of the machine. So it is important to understand the fact that we as physicists, we convert measured charges to dose. So to round up, we need to understand what are the role of physicists in radiation therapy. So as physicists who have interest in radiation medicine, who have interest in radiotherapy, it is important to note that we are important in performing shielding calculations. The housing for the equipment, calculation needs to be done to ensure that the structure is strong enough to attenuate radiation photons in order for safety of personnel to achieve. Also, we need to understand that physicists participate in procurement process.
Hello, sir.
The output of the machine.
Sorry yes, to interrupt your lecture, sir.
Okay, my time is up.
Yes, however, I would like to, yes, we've exceeded our allotted time.
Okay.
We would like to, can you please just round up in 30 seconds, sir?
Yes, yes, of course, in 30 seconds. So physicists perform environmental radiation monitoring. They coordinate personnel radiation monitoring, involved in teaching and education of clinicians, radiation oncologists, radiographers, involved in research and development in order to improve and optimize cancer care. So essentially, physicists who work in radiation oncology try as much as possible to ensure that the dose that is prescribed, that is intended for treatment of a given cancer tumor, is achieved. So that is why it is important to know what the machine is able to deliver in order to be able to quantify what is coming out of the machine and to determine how best to deliver the dose. So physicists play an important role. I will be available for questions. I'm sorry I've exceeded my time. Thank you for your attention. So these are the relevant courses and my conclusions. Thank you very much for listening.
All right, thank you very much, sir. I would like to appreciate your efforts, sir, and this beautiful lecture. Thank you. Also, I would like to apologize on behalf of the organizers for encroaching beyond